Morning, everyone. Welcome to another episode of Xa Talk Show. Today we are going to do Advent of Code, Day 5. Is it Day 5? Yes, Day 5. So Advent of Code in Wolfram language and Day 5, okay? And today I hope to do 2 or 3 of them. I hope to finish 2 or 3 problems in 1 hour while I explain things, okay? Start Wolfram language. So if you are new here, let me mention that, let's magnify, okay? Start the Wolfram engine 3, okay? So if you are new here, just go to xali.info, okay? xali.info. This is my website, and I have lots of programming language tutorials, Wolfram language, Emacs, Lisp, Wolfram language, Emacs, Lisp, those are good ones, and Unicode for programmers, everything you need to know about Unicode, HTML as well, introduction, and Visual CSS, okay? So you can learn, I've been coding for 30 years, and JavaScript in depth. This is the best JavaScript tutorial on earth, according to me. But I would say there are top 3. This is among top 3 JavaScript tutorials complete. I spent 3 years writing this, reading, all the JavaScript spec. Okay, and all my tutorials are written in a way that's easy to understand. Every paragraph has an example, standalone example. You can run it, and in this, no nonsense, no talking about how you should use open source or how you should use patterns or how you should use object. Everything is concrete. Exactly what you type, what it happens, what it does. All my tutorials are of that nature. In a sense, you can say it's a mathematical way styled tutorial. But when you say the word mathematics, people get scared. They think, oh, it's going to be monad, and they don't, no, it's not like that, okay? And no ninja, no zen, no storytelling. Oh, I've been programming C for 10 years. Then I went into small talk. Then therefore, Python is this way. No such thing, okay? Just concrete, everything, all my tutorials are of that nature. So JavaScript, and of course then you can use SVG, which allows you to have graphics, interactive graphics online, in particular charts, and PowerShell, which it's a best shell, okay? It's a best modern shell, PowerShell, much better than Bash by a magnitude. Then Golang, my favorite low-level industry language. This should be C and C++ should be wiped out. And I would also say Java. They should be just wiped out. Okay, Golang, I stick with Golang. Rust is not my thing. It's one of the fad today. But I got a lot people asking me what do I think of Rust. I don't know Rust, okay, but I don't think it's that good for lots of reasons. Golang, okay, simplicity, concrete, simplicity, simple and fast. Very simple. Golang is in fact simpler than Python, simpler than Python, then PowerShell, then JavaScript. JavaScript is most complex, okay? Golang is simpler than PowerShell, Python, JavaScript, simpler than Emacs, Lisp even, and simpler than WolframLang too. Okay, Wolfram, it's simpler. So Golang, and it's widely used. You get a job if you master. You want to master, start a project with the Golang. Okay, so, and Ruby is more elegant than Perl and Python. Python, Ruby, Perl is the same class. Python, I also have a tutorial on Python. And Porray, this is the old classic nerd thing. It generates rendered, ray tracing, rendering. So there's a tutorial on ProRay and others. SVN is basically obsolete, replaced by Git. And I also have a tutorial on Git. There it is. Okay, and there's Linux, of course, very practical. Okay, so today let's do and lots of other things, commentaries on programming language industry, on hackers, on the hacker culture, on the programming industry culture, and jargons and that documentation. Lots of essays on documentation. There's it's a field of technical writing, and plus my commentary and technology in the past 30 years. The progress of technology, today we have YouTube live streaming or cell phone, iPhone. So that's what made this talk show possible. And I'm also on Odyssey. Subscribe me there. Okay, Odyssey is a good thing. And then I begin with mathematics. This is my old stuff. That made my website the most popular. Lots of mathematics. Okay, so let's start to do the advent of code. And this time it's probably going to be boring for you guys because I'm just gonna focus on coding it. Okay, let's start a Wolfram language. Is there anything anything else I want to cover? No, I think that's it. Okay, check audio, check video, check. Okay, so and there is my Xadi Discord. Join. We talk about real life stuff. So if you join, preferably you show your real name and real photo of yourself and talk about real life stuff, not memes or not just like staying remote and real life. Okay, so Wolfram language. So today I'm going to try as many problems as much as possible. Okay, so yesterday so if you go to my website xadi.info, then you go down, there's Xa Talk Show. That's the index of all of my talk shows for the past 3 years since I begin. So the earliest is something like 2019 January. There might be a few actually before, but anyway, 2019 is when I started to do every week at least. Then about 2 years ago, I started to do exclusively live stream. I don't do videos, I just do live stream because I prefer that way. Live stream is more genuine. I talk, I talk, you listen, I see your chat. It's more genuine instead of 15 minutes, 10 minutes focused on a topic, a tutorial. That is very good as well, but so people can learn things. But I prefer live stream. 1 hour long. So there's a real human interaction going on. So yesterday we did Advent of Code, day 1, day 2, day 3, day 4. All the solutions, for example, yesterday is one single line in Wolfram language. So today, let's begin. This is my drinks, apple juice and tea. Comments and questions posted. So Advent of Code, you have to go to this calendar thing. Return to your Advent of Code calendar. So number 5, Number 5. I haven't read the problem, so live coding. real time trying to solve the solution. Day 5, okay? The expedition can depart as soon as the final supplies have been uploaded from the ships. Supplies are stored in stacks of marked crates. But because the needed supplies are buried under many other crates, the crates needs to be rearranged, okay? The ship has a giant cargo crane, you know, capable of moving crates between stacks. Okay, supplies are stored in stacks of crates. Okay, so you have a crane moving the crates between stacks. So it's almost like a Tower of Hanoi programming exercise, which is very interesting. If you don't know, look up Tower of Hanoi programming exercise. Okay, so stacks, crates, moving crates between stacks to ensure none of the crates gets crushed or fall over. The crane operator will rearrange them in a series of carefully planned steps. After the crates are rearranged, the desired crates will be at the top of each stack. Okay, so you have something at the bottom, you need to move them to the top. But when you move, you can probably only move the top one. So it's like a stack problem, exactly. There's a data structure called stack. So the elves don't want to interrupt the crane operator during this delicate procedure, but they forgot to ask her which crate will end up where, and they want to be ready to unload them as soon as possible so they can embark. Okay. So they do, however, have a drawing of the starting stacks of the crates and the rearrangement procedure. Okay, so here is your input. Okay, so we have like 3 stacks, I suppose. 1, 2, 3, 3 columns. Move 1 from 2 to 1. Okay, move 1 from 2 to 1, 2 to 1. Move 3 from 1 to 3. 1, 2, 3. Move 2 from 2 to 1. Okay. Move 1 from 1 to 2. Okay. So the result will be, the column 2 will be N, M, I suppose. So in this example, there are 3 stacks of crates. Stack 1 contains 2 crates. Crate Z is at the bottom, and crate N is at top. Okay, stack 2 contains 3 crates. They are crates M, C, D. Check. Okay. Finally, stack 3 contains a single crate P. Check. Okay. Then the rearrangement procedure is given, which is this. Okay, in each step of the procedure, a quantity of crates is moved from one stack to a different stack. In the first step of the above rearrangement procedure, one crate is moved from stack 2 to 1, 2 to 1. Yeah, the move number 1. Okay. In the first step of the the resulting in this configuration, exactly. So here are the procedure, which is an algorithm. Okay, and those English words can be considered the programming language. Okay. So in the second step, the 3 crates are moved from stack 1 to 3. Let's see, second step, move 3 from 1 to 3. Okay, like that. Okay. Crates are moved one at a time, so the first crate to be moved, D, ends up below the second and third crate. What? Okay, right. So step 3, move 1, 2, 3. 1, 2, 3, okay. Yeah, so D is on 1, so yeah. Okay. Crates are moved one at a time, so the first crate to be moved, D ends up below the second and third crate, okay? Okay, there's a... Anyway, so then both crates are moved from stack 2 to stack 1. Okay, again, because crates are moved one at a time, crate C ends up below crate M, okay? Finally, one crate is moved from stack 1 to stack 2. Okay, that's, yeah, okay. So this problem is exactly like Tower of Hanoi, at least so far. So let me show you if you don't know. Which is a fable from the Bible, okay? Tower of Hanoi. Let's look. I mean, as far as I know, there's a story in the Bible that's the Tower of Hanoi. So allegory to some stories in Bible. Why? Because this is advent of code, which is a Christian thing. Okay, so you know this is a puzzle. Basically, your goal is to Tower of Hanoi is to move this stack of disks from one pile to the other with one rule. At all times, there must be no bigger disk on top of a smaller one. And you can only move one disk at a time. So this problem, the essence involves kind of like, involves binary number, kind of, the principle. Okay, so this problem is basically similar. Let's see what is exactly the problem. So the elves just need to know which crate will end up on top of each stack. Which crate will end up on top of each stack. Okay, so you want to know the end result of the topmost one of the 3 columns. Okay, in this example, the top crates are C in stack 1, M in stack 2, and Z in stack 3. Okay, so you should combine these together and give the elves the message CMZ. Okay. So after the rearrangement procedure completes, what crate ends up on top of each stack? Okay, this problem is very easy. So you're given a stack of original configuration, and you are also given a source code algorithm of the procedure. Okay, and the problem is, you know, if after following the procedure, what's the result essentially? So in other words, what is the result after you run the code? Very interesting. So it's not, you know, it's a bit different from Tower of Hanoi, but the kind of the game is the same. The rule is the same. Okay, let's close Tower of Hanoi. So basically, you can think it's almost, you know, let me go elaborate. It's almost like given a input and given a program, you want to run a program and see what is the result. That's kind of the computer science way of putting it. But in practice, you just want to... Okay, let's think about how do we do this, okay? So 3 stacks. So you begin with input. So obviously, this is the input. You need to parse it. Okay, X input. Let's say it's a string like before. God, very annoying. You know, one of the issue with the advent of code is that it's a coding problem. It's a coding challenge. However, it does not require you to submit the code, nor does it specify exactly, in terms of technicality, what exactly is the input. It just tell you that this is the input. You can use a spreadsheet. You can find the answer in any way you want. So I mean, the point is, it doesn't say this must be a file. It comes from a file or a string, or at least it doesn't say. So, but so far we assumed it's a string. But in this example, if you assume it's a string, it's gonna be very complex because you have to parse this. You have to parse this into a stacks. So it's not good. So the easier way is actually to already begin with a algorithm. Wait. Okay, so for example, we can start with the algorithm. Let's say stack one is n z. Okay, for example, stack 2, we can start that way. DCM. Okay, and so on. But that may not work because you need to know what is the input. So let's see. Get your puzzle input. Let's see what is the input. Okay. Oh shit. Fucking shit. So so if the input is like that, you actually need to parse it. Because you cannot manually, write this out. So let's copy the input. Save. Wait, I don't want to save here. So hold on a second. Let's go to talk show. Today's talk show. Go to diet. And here's advent of code. Open a new one. Copy that. Close. Save this as advent of code input. And this is day 5. What? What? Day 5, okay, so here is day 5's input. How do we turn this into actual data structure? God, this is not sure I can finish more than one problem today. You can cheat just by manually create a list of 1 to, and with the Emacs, with help from Emacs, you can somewhat do that much easy. You can easily do that. Turn this into a whatever programming language's data structure. Basically a list of lists, a list of 9 items. Each one is a list. But which would work. I mean, because the advent of code doesn't specify you need to pass this string. But since we are doing coding challenge, we should think of some better ways. How do you? Okay, God, how do you pass this? Okay, this is not easy. Advent of code day 5. So hello guys, good morning. Arnold, secondary account. Use a 2-dimensional array. Second part of day 5 is easy. Okay. So Splendid is a expert of PHP, professional expert. By the way, PHP is a language laughed at by a lot of hacker types. But actually, I think PHP is good. I called it PHP. I pretty much mastered it 15 years ago, but I haven't coded since. But PHP improved a lot. Anyway, so So how do you pass this? How did you do it, Mr. Splendid? Let me think about this. Yeah, two-dimensional array, but the problem is how do you have to pass it. Or of course you can cheat. If you cheat, then you can say, for example, let's add this, let's add this. Let me do this again. So if we are going to cheat, it's easy. Wait, let's just say 0, okay? 0, that's cheating. We just add this, we just fill in the ones that doesn't have, then you have a structure, rectangular ASCII text, then you can easily manipulate. You can, you have to do that. Okay, for example, this is kind of considered cheating, okay? I mean, not really cheating because it doesn't say you have to do a certain way, but you can do it this way. But the problem is, then this is not good, because the problem is, the point about programming is that suppose the input is 1,000,000 columns and the stack can be 10,000 crates. What you're gonna do? You are not going to manually, do it. So that's not a good solution. If the input is this string, then it's super easy. It's super easy. You just split the string into a list, then you do a transpose, then you drop the first row, then remove the bracket, find replace, remove the bracket, then put a string. That's it. You got the data structure, and then delete those zeros. Then you got it. But that's not. So how do you? Is it possible? Yes, it is possible. But how do you do it? So again, split string is the you split the string, and okay, so hold on a second, okay. Let's copy that, okay. Let's copy that. Go back here. What is this? Day 4. Okay, it's yeah, today is this one. So yeah, let's put it here, and let's remove that, save it, copy the file path, close it, open it. So here is the input, okay, showing browser. So our problem now is to figure out how do you parse this thing. Okay, suppose chunk 4, filter non-letters transpose. Oh, good solution, excellent. So what you do is that you for each string, first of all, you split into by new line characters. So you got lines, a list of lines, each one is a string. Then you just consider each 4 characters. That's it. Thank you. Fantastic. Okay, let's start coding. Let's start coding it then. Yeah, okay, so the input, yeah, so the input, let's not worry about that. Okay, delete it. Okay, first let's work on this part. Okay, so we know how to do that for the input. So we got a list of lists. Each list is a stack. Now the second part, move one. So that is about the algorithm of. So you want to turn this. So what you can do, one way to do it is to turn this procedure in English into, translate this procedure into your language. So this move 1 from 2 to 1 will just become, for example, in Python or something, yeah, it will just become pop, pop list, let's say pop stack from 2 to 1. So pop stack 2, second stack, okay? Or you can, in Python, you just write something like that. Stacks. So the second stack, you pop it, then push. Okay, so in Python, you would do something like that. Pop and push that. So you just string manipulation, find and replace, use regular expression or whatever. Turn each one of these into the source code of your language. You are writing a mini compiler or transpiler. So you turn that English into this code, then you just, in Python, you just do eval or JavaScript or Lisp or Wolfram language. You can all do that. But that's one way. Another way is that, these are, all you have to do is to extract the numbers. Don't mind the word move from, just get the numbers 1 to 1. So, okay, let's start to write the code then. So that's what is, okay, so that's Python. Okay, let's begin to write it. So input, so first of all, x1, just like before, we defined a bunch of intermediate variables, okay? So string split, okay? Split by input and split by end of line character, okay? Then x2, you split again, this time by, this time by 4 characters each. So you don't call split. Instead, you call string partition. Okay, that's in Wolfram language. Okay, so right now, x1 is a list of strings. Each element is a line. Okay, that's x1. Now we want to, so how do you process each line? And you need to do that for every line. So therefore we need the map, just like yesterday, just like lots of event. So you want to map a function to the x1, one line at a time. And then you need to give a function. And this function, ampersand, that's a shortcut to stand for function. And pound sign is a shortcut to stand for the argument, okay? So this thing is a function, a lambda function or anonymous function. So this function takes one argument and it will partition, meaning that it will split the string by every 4 characters, okay? So let's count. Yeah, that's right. 1, 2, 3, 4. And let's make sure there is no off by 1 error. So 1 2 3 4 1 2 3, it's missing a character. Okay, but no problem. The string partition, when there is not enough string, you'll just ignore. I mean, it will just take whatever there is. Okay, so I think that's it. So first of all, let's do this and see what is the result. Close that to Wolfram language, paste it, run it. Okay, this is incorrect. Ignore those move from 2 first. So first of all, it's x2 becomes this empty, so incorrect. So what is the documentation for string partition? Non-overlapping substrings of length n. Okay, yeah, that's correct. But why is our function not correct? x1. What is x1? I wanted to show the length 33. No, this is not right. The length should be just 1 2 3 4 5 10 or something. So where did we go wrong? String split, input. Fuck. Why is it not doing? In fact, I can run this thing Emacs. Wait. I'm using Wolfram mod. You see, here's the result. I can run it in Emacs, but it's incorrect. Why is it incorrect? So first of all, we string split this input. Okay, string split by chunks of 4. Okay. Okay, then for each one we why is it not right? What? Let's just say what is x1. This is just wrong. Wait, string split. Now let's give it a. By default, it assumes a line, but now let's be explicit. Now it works. By default, it is a that is a default, an empty line here. But I don't understand why it wasn't working before. That's the correct answer. Yeah, that's the correct answer. Each element is a line, right? But why is it if you don't give that, it, let's see, split string pattern. Let's see, what is the default? Okay, so now you can see Oh, by default it's split by white space. So any white space become that, that's why. So now it's better. Now run it. Actually running Emacs. Fantastic. Okay. Now there are two parts of the input. One is the the actual input. The other one is a different input about procedure. So let's split them. Okay. So first of all, split by two empty lines. Okay. Then x in 1, imp 1, imp 2. Okay. Imp 1 will be x1, the first part. Okay. And imp 2 will be the second part. Then the first part, ximp1. Okay, let's just do it. Did we string partition it? Okay, so let's do it. What is the output of x2? String partition. What is x imp 1? Okay, that's correct. Oh wait, you forgot to do something. Okay, so once you split into two sections of strings, then you need to okay, you need to split string again. Okay, like that. Okay, then okay, that's right. Let's try it. Fantastic. Yeah, it's a list of let's see. No. Oh yeah, you forgot. This is not double N. This is single N. Let's do it again. Fantastic. This is the result we are looking for. No, it's not correct. NC, yeah, it just dropped. You see? Oh, you see, this advent of code, they actually try to be helpful because they add spaces at the end. It tries to make the problem easier for you. They add the spaces after that. But still, our code is not right. So because the first one should be 3 elements. For example, x2 x2, the first element. Okay, that's a empty string. Then let's say the length. Percentage sign stand for that last output, and slash is the pipe notation. So we can just say here length is 0. What the fuck? Okay, let's try this. Wait, it's a string. Okay, that's a function at. Let's see what we got. Shit, this is taking an hour. Won't work. String partition. Why is it? How many characters are there? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Oh, it automatically. The partition function, does it automatically drop the empty lines? So is there an option? Yeah, I don't know. No option. Okay, so sorry, this is taking a while. Why is it string partition? Yeah, so why is it not? Let's say 2. Let's say 3. What the fuck? You know, I wish Wolfram language would show the input form. Okay, so last output / input form. That should show the quote. Okay, let's do this again. Now let's say 3. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Now what happened to the last? 1, 2, 3. Oh, okay. So if there's not enough, then the string partition just drops it. No, okay, that's not. Let's say. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, when there's not enough, you'll just drop it. Not good. But even so, why is it? There should be enough. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay, that's not enough. Now what about the original problem? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. The original problem does have. Okay. It does have. So that means our code is wrong here. Let's copy the original. What? Fuck. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Show space, show empty space. 1, 2, 3, 4. 1, 2, 3, 4. Oh, yeah, okay, the last one is a return, that's why. So what you have to do, easy solution is to pad it. Pad is expensive operation. Okay, so okay, padded. String partition. Okay, string partition. Now you want to, before you partition, you want to say pad string. Okay. Okay, string pad left, string pad right. Okay, there it is. Make string to be of length n. Okay, padding it on the right with spaces. Okay, so okay. Pad right. Okay, we want padded to the right, and how many? Oh, the column also differs. What the fuck? The number of column also differs. In this example case, there's 3, but in the real input, it's 10 or something. So you have to actually find out how many. To make the whole thing completely programmatically done without any manual intervention, you need to find out how many columns are there. Okay, let's do fucking tedious problem. So okay, so let's just say x stacks. Okay. Process. Okay. So it's easier to read for people. Okay, so we have the input, and the input to become a list. Then we have stacks and procedure. Then x2 is the stack list. Okay, list of stacks. Okay. Okay, so and here we want to pad. Yeah, but before we pad, you need to know how many you need to know how many columns. So count, let's say that. Okay, so how do you get column count? You wait, this is not stacks, this is shit. This is not even stacks yet. This is just rows, lines. Okay, so this stacks is lines. So you have a bunch of lines, so you get the last line. Okay, last at the last line, which is this line. Then you split string. Fuck, tedious. You split it by empty space. Okay, then you want to get the last one. Okay, actually, so you can just say last again. Yeah, then you want to say to expression. Okay, okay, that's columns count. It's column count. Okay, then you get column count. That's you make sure you have column count times 4. Okay, so we have lots of variables now. you know, right now look at, you know, there are extra spaces there, right? Now let's remove them. So we actually changed the input, but our code is more robust because we will actually pad them to make them enough. Okay, so now stop showing white space. Now we have column count. Now string pad right, column count times 4. Then to make sure each line is of that long, then you string then you partition it, yeah. Then okay, then we can, okay, let's go back to Wolfram language, paste the code, run it. Beautiful. This is the desired result because there are 1 2 3 4 4, what is this? Yeah, 4 three stacks, but 4 lines, right? So now once you get this, all you have to do is you want to turn them into a array, you know, array of array. So easy, list of stacks. You want to drop the last one, okay? You want to drop the last one. Okay, there is let's see. Okay, so you can just say here, list of stacks, drop, okay, drop at the argument. Actually, you need, okay, so hold on a second. Drop the argument, last one, -1. So this becomes a function. Apply it, okay? So, you know, so this part we can write it this way. So this is, so the @ sign is a prefix notation. So here, that's a lambda, that's a pure function, that's lambda or anonymous function. Apply this function, applied at, you know, the rest, or you can put them inside the bracket. You can put this part into you know, the pound sign, either way. I mean, that's the advantage of the flexibility of syntax, you know, digression, okay? So now you dropped it, now you can put another function in front. We want to transpose, okay? Okay, that should be it. Let me show you, okay? So remember, before we have something looks like that, but now it actually looks like stacks. You see? NZ, DCM, and empty, and P, okay? So yeah, NZ, DCM, and P, okay? Now the next thing we have to do is we want to drop those that are empty string, annoying. Each one is 4 characters. Yeah, okay. Then so we again delete cases, so we can add another function. Let me show you here, okay? So we just call a function in front, okay? In front, and this function will be delete cases, okay? So this is argument, and the second argument will be a string 1 2 3 4 4 empty chars, okay? So now we don't need this, so copy all. So by the way, Zalpha, if you are watching, we were talking about doing this in scheme lisp. In scheme lisp, you can, so, Alpha also did one in Zephyr, in Fantastic, which is very practical scheme lisp. So, but what I mean is that you could, in scheme lisp, you can do something similar, like what I'm doing. All you have to do is just simply pipe lambdas, pipe, chaining functions, which is one of the most common idiom in functional programming. Okay, so now delete cases, let's run it. Okay, oh, we already did. Let's run it. What? It didn't delete. What the fuck? Let's try here. So here's the argument, and string 1 2 3 4, run it. It worked there. Why is it my oh, you need to map these to, right, you need to map this to each one of the items. So instead of at, you want to say map. Okay, copy all, back here, paste, run it. Fantastic. Here is our solution. Now let's see, what are they? Fuck, actually we have a lot to do. What is the, what's the length of the D? Let's see, 1. So wait, fuck. So list of stacks. Okay, list of stack last. That's one thing. Okay, length 1. Okay, but what is the type? What? It's not a string. What the fuck? So we are trying to find out the last one. Oh, it's a list. Yeah, so the last item is a list. Then the first item. Like that, okay. Then first item. Then it's a string, okay. Then you want to know the length. What? The last item, then the first item. Oh yeah, you don't want the true, that returns true. What? The last item, then the first item. Yeah, let's do this, okay? Let's see what exactly. Okay, there is a space. Yeah, then we have to chop the space, and also we need to remove the square bracket. Ah, fuck. This is a tedious code. And then we need to, this is not efficient. We need to do something to make them efficient. It's too much, lots of work to do. So first of all, let's make it clean. Okay, so let's remove the delete trailing string. Okay, so which command is the delete trailing space? Trim string trim. Okay, that must be string trim. there it is, string trim. Okay, so somewhere you want to apply string trim. Okay, so let's do it to no, we cannot do it there because lines becomes, so that's the number of columns. Oh, somewhere here, shit. Okay, so string partition. So after you partition it, let's do it here so you can easier to see. So pad right, then partition it. Okay, then you partition it, then you map it to lines. Okay, once you partition, okay, we can kind of add it here. So let's see. It's getting more complicated here. So string trim map. Okay, I think that's it. Let's do it. Then the delete case is just the delete case is just empty string. Okay, let's copy it. Yep, it's perfect. Perfect one-shot coding. Oh yeah, and then we need to replace the okay, yeah, we need to replace the string replace. Why is it not? Shit, Wolfram language crashed because the help window, I think there's a bug. Whenever you open the help window and try to enlarge, it crashed. Okay, anyway, good thing that I was working in Emacs, so we have all the code here. So now string trim, yeah, string replace. Okay, string replace. Okay, showing documentation. Yeah, showing documentation. Turn on JavaScript. String replace. Okay, string replace something, and we want to replace. What we want to replace? We want to replace. Oh yeah, multiple replacement. Okay. Left bracket by empty string. Okay, that's one thing. Then right bracket by empty string. Okay, yeah, so this is our function. Make it into a function, and this is x is the argument. So we want to play this function here. So the code is becoming extremely advanced functional programming. Okay, the code here. Let's see where I want to place it. Trim string. So you want to do that, yeah, to each and every item. I think that's that. Okay. Copy it back to Wolfram language, paste it. So here is our code. Let's see. String replace. Okay. So first of all, so the code, let me go over. Okay. So what you're doing is first of all, you do a map. So you map this function to list of lines. Okay. So this function will apply to each line of string. Okay. So it begin, so what does this function do? It begin by pad it to the right, adding space. Okay, make sure there are like number of count plus times 4 spaces. I mean string length. Then you partition it by 4. Okay. So you got a list of strings. Okay. Then you trim each item. You got a list of strings, so you do string trim and /add, that means map. That's a shortcut for the map. For the map here. Okay. So then you apply string trim to each one of the stack thing. Then you map again. This time you do string replace. Okay. You replace the square brackets. So actually that step can be shortened, so we don't have to map twice. So we just put string trim here. Okay. Okay, so the result, once you got the result, you drop the last row, because the last row is just numbers. Once you drop it, you do a transpose. You do a transpose, so row become columns, column becomes row. So you actually got a list of stacks, vertical list of stacks. So after you transpose, then you apply the delete cases empty string to remove those empty stacks. Okay, that's what it is. Copy all, paste, run it. Beautiful. Now it's beautiful. Each one of the stack item create is just a single character. Okay, so NZ is the first column. Okay, the first vertical, the first, how they call it there, the first stack. Yeah. Okay, so it's Wolfram language. Okay, we already did almost 80 minutes back. Okay, so yeah, we got a list of stacks. Now what's next? Oh fuck. Then you have to Okay, you have to. Okay, let's. I hope I can do this quickly. So how do you turn this into code? Okay, so that's what you have to do. Okay, so here's a procedure string. Then procedure string. You know, you want to turn this. So what do you want to turn it into? What you want to turn it into is, let's turn it into the Wolfram language code. So okay, so what you want to do, move 1 from 2 to 1, push and pop. Okay, so let's see. Wolfram language doesn't use this push pop kind of jargon. It uses append and prepend and delete. Let me show you. Okay, so go to the Wolfram language tutorials I have written. Then you go to list, position in a list, get elements, add elements, delete elements, change elements. Let's see, add elements. So you can use insert. So but what we really want is push and pop, because that's for stacks. We have a variable that stands for the stacks. We want to, yeah, okay, so you can use append to, you can use, these methods are not efficient in Wolfram language, because Wolfram language, each list, whenever you add item or remove item, it has to regenerate the whole list, so it's not suitable. If you really want a stack, you have to, there are other methods. So if you have, a real life programming problem where your stack is thousands of items, I mean, you need to constantly push and pop, then you should not use a list. Okay, you should use other ways. You should not use any of the prepend, append, because that's very inefficient. That's one of the flaw. That's one of the major frequently asked questions. If you do that, it's gonna be very slow. But of course, for this toy problem, even thousands of items, there's no problem. I mean, but in real life, you have millions of push and pop, and it's no good. So anyway, so what are we? So we want to turn this. Okay, so push pop is one solution, which is append, prepend to. Append, prepend, return a new expression with new item added. Okay. Yeah, and also Wolfram language, when you push and pop, it doesn't really just return that item, because that's procedural programming that do that kind of thing. I mean, the very concept of push and pop is procedural language thing. In functional language, you don't do that. So how do you efficiently implement a stack? Actually, I never thought of it in functional language. Well, I mean, you can do nested list. That's what, yeah, the real data structure list. That's what it's for. So so what you have to do in Wolfram language is you started to nest list, where each list is 2 items. Yeah, then it becomes just like Lisp's cons. But anyway, so let me look into the problem. So delete element, so you can drop. Okay, this stack is not a good, the push pop is not a good idiom here. Yeah, this push and pop shit. push and pop is not a good idiom in Wolfram language. So what should we do then? So change element, replace part. No. Okay, so actually I have to think about what's the best way to do a stack in a functional language other than using cons, nested list. Cons is not good, you know. It is not good in okay, so I don't want to use cons. I don't want to use to implement nested list. So the other alternative in general is just use a vector, so-called or array. In C language jargon, you use array, which means a fixed length thing. So in this example, depends on how big is a stack. It doesn't actually say. So you might, have a fixed stack of 1,000 items. That's not a good solution either, because this is, well, okay. I think what we're gonna do is just use push and pop. Okay, just inefficient. Okay, so first of all, pop. What do you want to do with pop? Pop is drop. Wolfram language doesn't really have that. There's no one single function that returns the item and, so when you do push or pop in other languages, when you do pop, for example, in Perl, in Python, in JavaScript, when you do pop, but in Wolfram language, that would become two things. That would become delete or drop plus get the first item. Okay, well, fuck. Delete by position. Okay, so which one should I use? Drop or delete? No, because these are functional, so they don't actually modify the variable. So you actually want to use append to. Prepend to. Let's just say this, okay? I'm getting too slow here. Okay, that gets the first item, and drop. Fuck. this push and pop is really a pain in Wolfram language. Okay, can you use some other data structure for the stack? I mean, in Wolfram language, what is the best way? Actually, this is a good question. I never thought of. What is the best way? What is an efficient way to implement a stack in a functional language, but without using nested list, without actually building a nesting of list yourself? Well, the obvious answer is vector. You have a fixed length vector of a big fixed length, but you have to know what is the length though. Yeah, but the problem is you don't know the length. So then you have to presume a length. Then if it's beyond, you extend it. Then that's cumbersome. That's like implementing a whole smart array, like in Python, Ruby. Oh yeah, so you can use sparse array. Oh wait, so in Wolfram language you can actually use, because it's a term rewriting system. Yeah, I can do that. Yeah, so this is very boring for you guys, I suppose. Let's see. Oh shit, I do have 4 people watching still. So what do you guys say? Should I go all the way, dive into the depth of Wolfram language? Or should I, I'm just mumbling actually. I should really just solve this problem. Okay, so right now I have 2 choices. Simply get it to work, use whatever, it doesn't matter, it's inefficient. Or actually use the efficient way, the proper Wolfram language, idiom to represent a stack. So, but if I do that, I still need to think about how though, because it's not very obvious. There's a stack. Let's see, can you use sparse array? Not really, because you really need a stack. It grow and shrink arbitrarily. You really need a stack, and but you can represent a stack. For example, let's say SS, let's say ST, let's say SS. You can emulate a stack by just do something like that. First item, this way, you are adding, let's say A, B, C, okay? This way, this is how you add, let's say, stack of 3, A, B, C, C on top. You can emulate a stack this way. This way, you are actually defining, wait, not 2 brackets. This way, you are technically, what you are doing is that you are saying a function, whatever xst argument, when argument is 1, equals to A. So it's using a term rewriting system. Whenever you see this, replace it with A. Whenever you see this, supposedly a function with argument of 2, you replace it with B. So you are essentially defining many functions with a single constant given argument. But this way you are emulating a list or a stack without actually having a data structure of a list. So this way they don't need to be consecutive. You can just have that with the missing stack. So but what you need to keep track your your indexes. That's you have to manually. So to append the item, let's say append a new, or you have to say is 4. Let's say x that's you have to keep track of this index. That's how you do append. And to do push, okay, let's say push. And to do drop, you just say, to do a drop, you just say not so easy though. Okay, you can do it. You can, okay, to do a drop, all you have to say is that yeah, so this is how you do drop. So let's write it out, okay? And this is okay. We are actually, I'm not doing good here. I'm just digressing into something else. WolframLang has drop first. Okay, so Wolfram language has drop and first, that together they are like pop in most languages. And you have prepend and prepend too that are like push in most languages. However, like Python and Ruby, okay? So Wolfram list is like a smart vector. It's not actually smart array, okay? Just like Python and Ruby. And it is inefficient if you constantly need to push and pop and push, change the length. Thousands of times, okay? That is so we can, a efficient way to implement stack is by a fixed length array of huge size with empty slots 0 or such, okay? But the problem with that is that you have to have an estimate of what is your length, okay? for this problem, we can actually, I'm kind of just digressing, but this problem, let's see what's the input. Yeah, that's small. You can just say each one is 50. Yeah, they'll solve it, but but I'm digressing. Okay, so but another way, more advanced, to implement a stack is by using the term rewriting nature of Wolfram language, okay? And it will be something like this. Example stack, okay? So let's fuck. I failed in this problem. Okay, something like that. Showing browser. So this is about stacks in Wolfram language. Yeah, okay. But yeah, I'm just wasting time. So let's just do the normal way. Let's just use the inefficient way. So now we got a stack. So we want to translate into the Wolfram code. Okay, so let's start to translate this English into Wolfram language code. So move one from 2 to 1. Okay, move. So the first number is how many times to do it. Okay, the second number is the number list. Okay, so list of stacks. So okay, so move 1 from 2 to 1. What is the code? That means, so from 2, so this is the second list of stacks, the second stack to the first stack. So how do you do that? So you want to pop this, okay? So pop is drop, okay? So Wolfram language drop first into n, okay? So yeah, this is very tedious because Wolfram language is a functional programming language. It doesn't change variables. So this drop, they just return the new result. So when you want to do this, you have to drop it, get that first item, then save the dropped result into your list of stacks. Then push that item into the second, stack. Then you have to save your list of stacks again. Back. Okay, so it's almost 2 hours. Fuck. Shit. I failed here. Basically this so far, how do I, is there some other way? Wait, so move that from 2 to 1. Is there some other way then? Okay, I think I know a better way. So you see, I found a better way. I found a much better way suitable for Wolfram language. Is that true? Yes. So instead of using stacks is actually very natural in the standard structure. But instead of using stacks, you see, notice the number of crates never change. The number of crates never change. Okay, so you can consider the whole list of crates as one single list. you never shrink or increase the crates, the list size. You never change the list size. So you need to have a separator, between the columns. So you just add an empty thing, let's say 0, to indicate where each crate separates. But if you do that, so remember, the list of crates never changes. So that actually, in fact, the list, the number of crates can be your stack size, the maximum stack size. That's right. Fucking shit. So that can be your maximum stack size. Yeah. So in fact, so we can go back to using the array idea. So okay, I want to solve this. Okay, so what do you do now? Okay, here's what we do. Here's what to do. Okay, so let's just first let's equals to drop. Okay, so yeah, this is extremely inefficient. This is extremely inefficient what we are doing here. Move 2 to 1. So it's just first. Yeah, this drop and take is not good. 2 to 1. So drop first. Prepend. Okay, so actually, this is what it is. This English translates to that. Very, very inefficient in Wolfram language. Let's see what is prepend argument. Expression and element. Okay, so expression first. Okay, so that's what move 1 from 2 to 1 means. And you need to loop this, because if this, when you comes to move 3, then you need to do this 3 times. So very bad, very, very, this is extremely inefficient. So I don't want to do this, okay? And extremely inefficient, the code is also extremely ugly. This is not, again, push and pop, they are not functional programming concepts. You don't do that in functional programming. But actually, I never thought of what is the equivalent though. Well, okay, the way is you just create nested list, just like list cons. Okay, I don't want that. Let's think about the other way. Now let's think about the idea that the number of crates never change. Well, if you do that, then it's about shuffling of the zeros. Let me show you an example. So if you have A, B, C, D, let's say, okay, N, Z, D, C, M. So that's one way to represent this stack. So in this way, all you have to do is just shuffle those, okay? So 1, 2, 3, 2, 2, 1, 1, 2, 3. So oh God, I need to go to the bathroom. Anyone still watching? Okay, let's take a break then. Now it's almost 2 hours. Let me take a break and be right back. Yeah, I want to finish this problem in the most efficient way possible. And yeah, and more general, I want to do that. That's the point of doing these exercises, not just to get the answer, okay? So I'll be back in 5 minutes. I'm back. Okay. Two hours already. So there are several ways to go. Now the problem is implementing a stack. So there are multiple ways. Okay. This turns out to be a more kind of general problem. So let me just go full out then. The problem requires implementing the data structure of stacks. Okay. It requires n stacks. Not just one, but n of them. And stacks is not a good data structure in functional programming languages. Such as WolframLang, because it requires change of data variable. Okay. Okay. And it's not a good data structure in functional programming languages. Okay, because it's not a good data structure. But I suppose most programming languages, they have a way already, functional programming language, they already have a idiomatic way to represent the stack. Okay, so anyway, one most common way to implement stack in an efficient way in functional programming languages is by so-called list, aka nested list of two things, aka Lisp-con. Okay, that is the standard. The standard way to implement stack in an efficient way in functional programming languages is by nested list, linked. It's called linked list. Okay, that's Lisp-cons. In fact, in Haskell, that's the way you do it too. As far as I know, I don't know Haskell, but I know a little bit. You don't have arbitrary. You don't have a list in Haskell. You have to implement it by linked list. Okay. So can we do that? Yes, of course we can do that in Wolfram language, but I've never done. Refresh. Okay. Okay. What? okay? No, it's something else, okay? In functional WolframLang is by linked list, okay? So we can do that, or alternatively, we can implement stack by a fixed array with a fixed size length, okay? And in this case, we need not just one stack, we need multiple stacks. Okay, so it gets tedious. And by the way, this can also be done. I was going for a walk, so this actually can be done in this way, okay? You know, represent that. That's right. 2, 2, 1. So 2, 2, 1. So 1 is 2, and move 1 from 2 to 1. Right? From 2 to 1. From 2 to 1, so prepend to 1 by taking the first item of the number 2, okay? Then the second stack 2 to 1 is just drop the second stack. Yeah, it can. So yeah, so these two lines represent that thing. Or you can also do it this way. Double check. 1, 2, 3. 2 to 1. Yeah. 1, 2, 3. Yeah. You can do it this way or do it this way. This way is more efficient than that one because that one requires, you see, the first from 2 to 1. Actually, so this is incorrect. What? So the first stack is 2 to 1, so the third one doesn't change, okay? So here's the third one that doesn't change. The second one is dropped 1. The first one is you get the first of the second one then you prepend it to the first one. So you can do it that way or that way. The second one is more efficient, but both of these are very inefficient because you are changing the structure multiple times. Not functional programming friendly. Okay, so we are doing a stack. So we talked about stack. How do you implement that in functional language? So one way, the standard way is a nested list. So how do you do that? Well, in Wolfram language, you can say yeah, it's take 10 minutes, take 5 minutes to code it, to create a data structure of a nested list. Yeah, we can do that though. We should do that. But there are also different ways to solve this problem. So you can use nested. Okay, let's go back to writing it out. So let's see. So we need multiple stacks. Okay. Ways to implement a stack in a functional programming languages. Okay. You can use a linked list, or you can use a fixed array with a fixed length. If you want to do that, the problem here use 0 to indicate empty item, empty slot. Okay. The problem here is when you want to push or pop, you need to find where the real item begin. So for example, you can keep a index to indicate where the real item begin. Because when you pop, that means replace the first item by 0. When you push, means you want to replace the last item by a new value. Okay. Pop means replace the first non-zero value by new value, and by 0, and return that value. Okay, so that's what pop means. Push means replace the last. Okay, replace the last 0 by a new value. Okay, so let's show in browser. Let's, we are starting to write a blog. Okay, the problem requires implementing the stack data structure. It requires multiple number of stacks, okay? Yeah. And stacks is not a good data structure in functional programming languages such as WolframLang because it requires change of data variable. Okay, so ways to implement a stack in a functional programming language. There are several ways. The standard way is to implement stack is in an efficient way is a linked list. Okay. And alternatively, we can implement stack by fixed array with a fixed length with 0 to indicate empty slot. The problem here is when you want to push or pop, you need to find where the real item begin. So for example, you can keep an index. For example, pop means replace the first non-zero value by 0 and return that value. Okay, but you must find it. So each time, maybe you have 1,000 zeros, it takes time to do that. So alternatively, you can create a constant, a variable that indicates what's the current stack, like a pointer, okay, the current non-zero value. Okay, so let's keep writing it. Instead of searching for the first non-zero, you can search it once, save it as index. Okay. Okay, so that's how you implement stack. Let's do this. By linked list is one way. By fixed array with 0 or other to indicate empty slot. Okay, that's two way. Now the third way, now that's two way to general to represent the stack. Now let's just think about write it out. In-term rewriting system is to use a particular symbolic sequence for example, let me just write this out. implementing Okay, we have now 3 ways of implementing a stack. Okay, so 3 ways: by a linked list, by an array with 0 or other to indicate empty slot, by a fixed array. Okay, or in term rewriting system, use symbol sequence to stand for stack and its items. Okay, now we can do, this is example of using fixed array and the issue we have to do. Then here's an example of using term rewriting. Let's see, let's just write this out. Okay, maybe that. Okay, can we do this? So this is one way to do it. Okay, so let's yeah, just fucking problem. Am I gonna finish this problem or not? If you want to do this, you need to manage a variable index. So yeah, it's a problem. So how do you implement push? Okay, this needs to work out. You know, it needs a lot of code to actually work this out. Okay. So that's no good. No, that's no good. So far, 2 hours. And why don't we? I mean, we could also just try to implement a nested list to start to write code, a linked list. Or let's just forget all about that and just use the drop and just use this. Yeah, but this is extremely inefficient and inelegant, and especially when you want to do this n times. So how do you do this n times? So let's do that. Do. Okay, this is how you do it n times. Yeah, do it, one time. Yeah, so we can do this. This is extremely inefficient. Oh my god, and the pen. So you see, move 1 from 2 to 1. So that 1 is indicated here. This do means just do this number of times. Okay, so do 1 and from 2 to 1. So 2 is indicated here and 1 is indicated here. In fact, if it involves 3, the code here will also change. So this is very bad code. Because you can tell because you cannot see, there's no structure, doesn't correspond to the numbers. You want a way to exactly correspond to the numbers. Fuck. In imperative programming language, it's just so easy. For example, you can do push pop, stack 1. Yeah, that's how you do. So for example, in Python, this is in Python, okay? And that's just that line. And wait. Pop stack list 2 to 1 and repeat. So you do a loop. How do you do a constant loop in Python? Common string loop, So constant loop, for loop, while loop, exit loop. While loop, there's no. Okay, we can use for in range. So let's write this in Python. There it is. For in range, so this is A, M, and P, okay? So do this M times for X in range, M times. Okay, you don't care what X is. So you do push, let's say you have a stack. Stack is just a list, right? And list is represented by what? A list, so square bracket stack. Okay, so you have to do it actually. So you have a list of lists. Okay, let's say you have 3 stacks. Okay, so all you have to do is push that and push stack from n pop. So pop n stack list n, and let's get this right. Okay. That's right. So stack list. Let's see if I want. Can we? Yeah, it's okay. So stack list. God. So stack list. Pop the nth stack. Can you actually pop? No. Well, in Python, you pop by its object-oriented fuck. So these methods, yeah. So you object-oriented fuck. So you say this instead. Pop, okay. And the push is, so you push that's it. That's what you do in Python, okay. Yeah, you stack list n and stack list p. That's Python code. Okay. Now the problem is just that in Wolfram language it's not suitable. Yeah, this is so bad demonstration, so bad. So bad because we are trying to line of code. I need to get back to doing those when college work slows down. Stopped on day 9 first, doing it in C. Oh my God, C. A real man's programming language. Okay, we kind of what am I going to do now? I want to solve the problem, okay? Let's solve the problem. Let's not go into, general philosophy and stuff. Let's solve the problem. Now let's just try to make this. So, today that's our solution. But now the problem is just the stacks. Let's try to make these somehow more efficient. Let's just let it be. So what you really need to do is to represent this thing, okay? You see, to represent that, this is what you do. And more in general, so move, let's see, how is this Python variable? Move m. Okay, let's fix that Python. This variable naming change, okay? Move p from n to m to n, okay? So this is gonna be p times, and this we don't use. That's a convention for variables you don't use. And here I believe that works in Python. Let's just say x, okay? So for p times, so pop m to n, okay? For m to n, do it p times, okay? That's right, that's Python, okay? move p number of times. Okay. So that's Python. Good. Okay, save it. Go back to the Wolfram language code. So move p from p number of times from stack m to stack n. The way you do that is you list of stacks m to n. So wait. Yeah, so we need to clean this up really. So yeah, so when you have a general variable, this doesn't work neither. Fuck. Move p number of times. So okay, so that is p easy. Okay, do p times from stack m to n. Okay, stack m to n. Okay, so all you have to do is, okay, yeah, now I get it. Stack m to n. So stack m and stack n both changes. Okay, so m and n, both of them changed. So the new m, so we want to do n first. So n will be appended from m. Okay, so yeah. So prepend the n by m. Stack m, the first item, prepended to the stack n. Okay, then the change for m is easy. It's just, okay, it's like that. So you have two procedures. Yeah. So actually we don't need, so simplified, so much simplified. So do these p times for each time you want to stack n. Okay, so you prepend list of stack, so from m to n, so from n m to one single n, then you drop the first item of the m. Okay, that's inefficient, but let's make it efficient. Okay, width is a local variable of constants. Okay, so first item. Okay, so you can do that. So we move these two inside. So first item is equals to, okay, equals to the first that. Okay, now yeah, this is still fucking inefficient. It's still fucking inefficient. Yeah, this is, you know, in Wolfram language or any functional programming language, you don't, the push pop is very problematic, unless you have a nested, linked list. Can you explain why it was inefficient? Basically because okay, so let me explain. Okay, so a stack is a data structure where you have a kind of array kind of thing, a list of items, but you constantly add an item to the front or drop an item. So you have two operations: delete an item in the front, sometimes in the back, doesn't matter, but let's just say in the front. Okay, so you can delete one item at a time. You can delete or delete more, or you can add an item to the front. So every time, so that's the two operations for stack, usually called push or pop. Push means add, pop means drop. Okay, and when you do pop, you also return that value, return whatever is the first item of the stack. Okay, push and pop. You can think of it as a stack of books or stack of dishes. You always take the first one, you put a new dish on top, you stack them up, or when you take them out, you from the top, stack. Okay, very common data structure. But when you to implement that, usually, so you need some kind of array or list. Depending on what language, they mean different things. But in terms of C, array means a fixed list, a fixed length. So when you have an array, fixed length number of items, you cannot change the size of the array. Okay, that's the case for C, for Java. You cannot change the size of the array. So if you need to push and add an item to the array, or if you need to remove an item, you essentially just create a new array. So suppose you have a stack of 1,000 items. Now you're gonna push one item. Okay, yeah, then in C or in Java, what happens is that you have to create a new array. What they say, reallocate memory. So that's a very expensive process. If you have an array of, let's say, 1 million items, it takes 10 minutes to do it. Okay, something like that. Okay, so you cannot change the array. So whenever you want to change the size of array, you have to recreate, like create a new array and replace the value of a variable, something like that. Okay, that is why that's the data structure of array in the low level C sense, the actual bits, the electronic, that's the way it is. So what do you, if you want a list that you can constantly append or prepend, things constantly change size. So to do that efficiently, you have several ways. Okay, in the Lisp tradition, what you have is a linked list. So in Lisp, you don't actually have a linked list. So let me explain what is a linked list. Linked list is just a nested array of two items. So you start with an array of only two items, never changes. In fact, in Lisp, in Common Lisp, in Scheme Lisp, in Emacs Lisp, that's a primary data structure. So you have it's called cons. Okay, so you have a kind of a thing that's made of two things. It's like just a fixed length array of two items. Okay, so if you want to add an item, you nest the second part, you replace the second part by another array of two items, cons. Okay, so now you can consider
you have a list of 2 items. It's hard to explain. It takes more time. So that's the idea. So creating a list, let's say 10 items. What you are actually doing is that you have an array of 2 items. The first part represents the first item in your list. But the second part is an array again of 2 items. The first part of that thing represents the second element of your list. And the second part of that array is again a nested array of 2 items, and so on and so forth. So you tail nesting this a bunch of array of 2 items. In Lisp, it's called cons, C-O-N-S. Okay. So, and at the very last one, the innermost one, array of 2 items, the last part of the array is nil. That represents, okay, there's no more. That's it. Stop. That's the end of this nesting, giant, huge nested thing of array of 2 things. So that's cons in Lisp. That's called cons in Lisp. And this kind of nesting, this way of nesting data structure is called linked list. Okay, it's called linked list. And in Haskell, so this is one way to have a efficient data structure, a list-like data structure where you can always add things and remove things, constantly push and pop efficiently. Because every time you remove an item, all you have to do is you just delete the first array. So you don't change anything. You just remove the first array. You just get this, remember, array just 2 items. You just get the second part. Ignore the first part. So that's how you drop. And add is very, very easy too. You just add another array. So constant time. So it's constant time. So but the problem with linked list is that you can only add to the front or drop from the front. If you want to get the nth item, then that's problem. That you have to start to count the index and see the nth nesting. The first element of the nth nesting is your nth element in your list. Okay, that is the linked list. In fact, this linked list thing, array, vector, what's the difference? That's a big topic. Okay, and it took me 10 years to actually really understand it. Okay, so let me just point you to Wikipedia. Linked list. Linked list data structure, Wikipedia. Okay, so there's so you see that each one of those squares is like an array of 2 items. The second part is again an array of 2 items, and so on and so on and so on. So a list, to represent a list or a sequence of elements, you actually just nest these cons. Very extremely idiotic. Okay, this so this allows you to very efficiently add one element in the front. Always just push or drop one element in the front. Very efficient. But if you want to insert to the nth position, that's not that's very inefficient. Or if you want to get the nth element, very inefficient, because every time you have to traverse this nesting until you reach that. So that's one way. That's one way to implement a sequence kind of thing. And the advantage with linked list is that you can quickly do push and drop efficiently. But if you want to random access, very inefficient. Okay, so another way is just with a standard array of size n, fixed length. You can never change the size. If you want to change size, the language has to recreate the whole array. So that the advantage is that it's very fast to get nth element. Okay, that's very fast to get the nth element. However, it's very expensive when you want to delete some element, doesn't matter in front, in back, or add something, insert something, because it has to recreate the whole array. Very expensive when the array is large, like 10,000 items. Okay, so so you can look at this article. That's about that array. Okay. So we are talking about different implementations for kind of a sequence or collection kind of thing. So array is one, linked list another one. Another solution, which is what Python, Ruby, JavaScript, their list, their so-called array. Each language have different names, but JavaScript, Python, Ruby, their list or their array is a smart array. So what they do is that they basically have an array of fixed length, but they keep a variable that indicates what's the current max number of items in the list. Okay, so if you are going to add an element, then it checks if that's beyond the current array size. If it is, then it recreate the entire array, very costly. But however it does that, it just double the size. So if your current array is size 8, and if you want to add one more element, then it's very costly. It sees, oh, it's beyond. So I'm going to create a new array of 16 elements, so a lot more room. I'm gonna do this one time. So yeah, it's slow, but I'm gonna do it one time. But however, I give you, 7 more extra space, so you can work with it. So those empty spaces, they just put 0. They put some special value, but they keep track. They keep track. What's the current max number, the actual number, but they actually have something hidden. You don't see it. So they represent these things. There's no proper name to it. I just call it smart array. So it's array, but with the wrapper, so you don't see the hidden element. So the advantage is of these smart arrays that it's very fast to get any nth element, and it's also fast to either append or prepend depending on how it's implemented. Very fast. But if you want to insert something in the middle, again, that depends on implementations. So, but basically they avoid recreating the whole array. So, but if you keep adding elements, let's say to the front or the bottom or the end, anytime it's beyond the size, it just recreate the array with a lot more empty values. So it reduces the number of times you have to kind of recreate the array. Okay, that's one solution. This solution is used by I think almost every language: Python, JavaScript, Ruby at least. Okay, smart array. They just call it. They may call it list or array. Depends on the language. Okay, smart array. In Wolfram language case, I think it's also a smart array. Okay. Yeah. So why am I first about this? Because well, it's just not. I shouldn't worry too much about it. I should have just coded this in the beginning and saved 3 hours of talking. Stretchy buffer. Oh, okay, that's a new term. So, okay, so this array, this data structure, actually this is, let me explain. This personal me for over 10 years, for about 15 years or 20 of my programming life. I don't understand it. Like what? Because this is not mathematics. Okay. Let me explain this one. This is one of my. It took me 20 years in heated argument with the fucking C coders and C++ coders about this, because this C C++, Java, this type of coders, they know this well. They are very excited about this, but they don't understand the mathematical concept. Let me explain. So mathematically, they are just a sequence of things. Why is it that, for what reason? What is the reason that when you have an array, the C array, fixed size, what is the reason where when you have an array, it is constant time, constant random access time? That doesn't make sense. I mean, suppose you got given an abacus. Abacus is a computer, or a Turing machine. Why is it constant access time when you have an array data structure? Let's say you want to get the 1 millionth item. Don't you have to move the needle, until it reaches 1 millionth, right? But that's not the case. So why is it constant? Nobody can explain this. These C++ idiots, they don't know. They cannot explain. But they can just tell you it's constant. Okay, that's just how computer works. The reason it works that way is because the way the electronics, the CPU, the memory, the way the memory is actually, because it's actually just parallel computation by nature. The way the memory is implemented happens to be parallel for array. Okay, so there is an article. Let me show you. So search for Xali array constant time. So this puzzled me for like 15 years, and eventually one day I found the answer. So this article, why is array access constant time? These compiler writers, they cannot explain. You read, in fact, just about all textbooks, even Wikipedia. You go to, you read array data structure. I have a screenshot of it. Okay, so it says they effectively, so why is the reason, why is it constant? Wikipedia says they effectively exploit the addressing logic of computers. That's it. Why is array access constant? So you go to Wikipedia, and it has, 10 pages about it. But why is it constant? The only answer it says is just this sentence. They effectively exploit the addressing logic of computers. What the fuck does that mean? An abacus is a computer. How is it? How does, you can have an abacus, it's consider each column as a array, the first row. How is it constant? Even with your fingers, you have to move, 1 millionth column is, you have to move all the way there. How is it constant? So Wikipedia says they effectively exploit the addressing logic of computers, which is not a good answer. What computers? DNA computer is a computer. Quantum computer is also a computer. What do you mean logic of computers? They mean logics. They exploit the addressing logic of electronic computers of the way we happen to implement the memory. That's what they actually mean. And even that is without explanation. So one day I found this, in 2016, I found this blog here. Okay. Why is indexing faster than binary search? By this Chinese guy. He's kind of famous Chinese programmer. Very famous, very popular among the China programmer community. Ying Wang, that's his name. He has a blog in English. Okay. He explained it. I read this. Oh my God! This literally solved a question I have for about 20 years or 15 years. Why is array access constant? Because the way the electronics, the memory implementation of the memory
so happens it's parallel, okay? It's just parallel computation. You don't have to count until the million, you just parallel the way electronic works, okay? You can see the diagram. So that is why array access is constant time. And this is not mathematics, okay? There's zero mathematics in this. It's not a mathematical property. It's just the electronics engineering happenstance, okay? On an abacus, is it true when you have array, it's constant time? No. On a Turing machine, is it true when you implement array, it's constant time? No. Okay? So this is just, it just so happens on the electronic digital machine, you have this. But however, all the textbooks, doesn't matter, algorithms textbook. I don't know about Knuth book, but you look at all the textbooks, data structure, they don't have one, they don't have one line that explains why. They just tell you that array access is constant time, random access. Okay, so this is the rant. This is why, I'm kind of stuck on this, because I don't want, because I have I'm trying to get over, I'm trying to find a better way to implement the stack. But anyway, today it's been 3 hours and I ranted a bunch, but I haven't solved the problem. Very bad. So thanks for explaining. Sometimes called vector. Yeah. So in Emac Lisp you also have vector, but it's not. In Emac Lisp and in Common Lisp you have a thing called vector, and that is just C array. So it's very confusing, So I have another article about what does list, array, vector, things mean in different languages. Anyway, basically because the address circuit in the CPU runs in constant time, okay? Yes, you have the address of memory of first position of the vector and first sum value. Okay, so that in one explains that adding two numbers of 3 bits would be the same time as adding two number of 60 bits. Yeah, I don't know the low level of CPU much. I started to learn about that. But anyway, so I want to end the video, but I failed in getting this, solving the problem of today. So does this work actually? Let's forget about that. I mean, does this work? Maybe I can finish in 5 minutes. Let's hope. Okay, let's just put that there. So does this work? First item equals to, so from stack M to stack N. So from stack M so actually we can so you drop it and then you list of stack, then you prepend, right? Yeah, I think this works. But okay, so even this works, then we need to convert, we need to write code to convert this string to this. Okay, so we need to convert that to that. Okay, yeah, too bad. That's gonna take another at least 10 minutes. That's it for today. Okay, yeah, new chance to learn. So it's too long today, 3 hours already. So that's it for today. Thank you guys for watching. Yeah, interesting stuff. Okay, bye guys. So what we have is a bunch of extraneous discussion. I'll have to many, but we have some very interesting questions today about how do you implement a stack in a functional programming language. In Haskell and Lisp, I know for sure they just use linked list. Okay, bye guys. Gregan, is you still here? Thank you.